Hello, dear students. Good morning to one and all. Today we will discuss that what is meant by multicollinearity and what are the causes and consequences of multicollinearity. A little bit we discussed last day. That is what is meant by multicollinearity and what are the causes of multicollinearity. So today we will discuss that mainly the consequences and how we can detect the multicollinearity. So generally, as you know that how we can find out the multicollinearity and what are the causes of multicollinearity last day we discussed. So just I'm going through that. See, as you know that multicollinearity means the when there is a correlation between the two or more than independent relation between the independent variables is called multicollinearity. So the multicollinearity nothing but, for example, if you take into account the multiple regression, so that is a y is equal to beta 0 plus beta 1 x1, beta 2 x2, beta 3 x3, and beta 4 x4. So see here, y is a dependent variable, x1 x2 x3 x4 are the independent variables. If there is any relation between the any two independent variables or more than independent variables, so that is called multicollinearity. So generally, if you take into account, sometimes they will use the covariance between the x1 and x2. There is nothing but the relationship between the x1 and x2 variable. If it is equal to 0, when you're finding that relationship between the two independent variables is equal to 0, so we can conclude that there is no multicollinearity. There is no multicollinearity. So if there is a covariance between the x1 and x2 is not equal to 0, it means that it may be plus, it may be minus value, not equal to 0. But we can find out there is some multicollinearity problem. For example, if you find out if there is any covariance between the x1 x2 variables, there is a plus or minus one equal to 1, nothing but, so the correlation between the independent variables are equal to 1, whether minus or plus. So there should be a perfect multicollinearity, nothing but there is a strong multicollinearity problem in our model. So that is the case we discussed. So graphically I will show you this is also. See, if you take this is a this circle is a y, there is a dependent variable, and this x circle is a independent variable, and another w is a circle is a another independent variable. So if the two variables related each other, this is a red mark. If you take this is a red mark, see the red mark portion, how much the portion is there, there is small when you compare with this. See this is another uh, model. For example, if you take this y circle is a dependent variable, so this w is another independent variable, x is a other independent variable. So when the x and w, they are correlated each other more compared with the this diagram. So here, when there is a correlation between the two independent variables, which is considerable, nothing but the modest, nothing but is a less. So when you compare with this one, see the portion is very high compared with this portion, the red mark, red color. It means that the two variables are correlated each other is more, nothing but the correlation between the w and x is high compared with the in this diagram, figure a 3a and figure 3b. So here the correlation between x variable and w variable is less compared with the 3b, right? This is we can identify through graphical presentation. Simple, we not understand only I'm showing this kind of graphs. So if you not understand, you can see, you can take this example. See, this circle is a blue circle is a dependent variable. So this circle is a x1 circle is a one dependent independent variable. The x2 circle is a another independent variable. See, the two variables are related each other. So how they are correlated each other? The C part. Okay, C part is called the correlation between the two variables. So if you take into account numerically, so this is a graphical method, but easy to understand. But when you're the data, if you take the time series data, so mainly in the time series data only we can get this type of multicollinearity problem. Whereas cross section data, you may get less problem, but nothing but you may get a less, nothing but when you use cross section data, you may not get multicollinearity. Less time only you will get multicollinear problem. But whereas when you use the time series data, generally you will get a multicollinearity problem. For example, I have taken this variable, the y variable, and x1 variable, x2, x3. Here y is the dependent variable, x1, x2, x3 are the independent variables. So when you run the relationship between this x1 and x2 and x1, x3, x2 and x3. So if you observe the data only, you can clearly observe that. For example, if you take into a relation between x1 and x2, there may be some considerable relationship, because see, there's a small difference. There is a difference between these values. Okay, 10 to 15, 50 to 25, 75. But there is increases, but there is a relation is there, but there is a less relationship between the x1 and x2. When you compare this x2 and x3, see, this is 50 and 52, then 52 to 75, then 52 to 75, then 75 to 90, here 75 to 97, 90 to 120, here 97 to 129, and 120 to 150, then 129 to 152. So here, when you run the correlation matrix, or when you do the correlation between the x2 and x3, you will get more or less equal to perfect collinearity, nothing but which is more equal to 1, nothing but the r square r value, sorry, the r value that is the x2 and x3 of correlation between x2 and x3 is more or less equal to 99%. You will get it. So when it comes to this x1 x2, you may get relation, but which is less than the x2 and x3 relationship. So for example, I have run that correlation matrix in Excel file, Excel software. See, you will get this kind of the x1 x2 relation is 19.58. So for example, if you observe this x2 and x3 variable, see 19.58 also. But we can say observe when you run the regression model, in order to know that whether the particular model has been suffering from that multicollinearity problem or not. So cleanly we can observe by correlation matrix. That is the one method to know that how is there any multicollinearity problem existing in our model or not. For example, if you take there is no longer perfect multicollinearity between x1 and x3. For example, if you take into account as I told you that x1 and x3, this one and this one. If you run the correlation matrix, you may get a less correlation, but it may not be no longer perfect, nothing but the two variables may not move together in the long run. So here there is no longer perfect multicollinearity between the x1 and x3. So however, the two variables highly correlated, because calculation will shows that the coefficient of correlation between them is 99.59. So sometimes if you take into account, when you take the short period, during the short period, they may have the perfect collinearity. In the long term, there is no multicollinearity, nothing but there is no correlation between the two independent variables. Generally, I may give the good example for you that when your course is started, so there is some relationship between the two friends. For example, if you take at the time of admissions, at the time of beginning of your course, you have the good friends. So after 1 month, the relationship may be break. Nothing but you may not continue with that your friend. So that during the particular period, there are close friends. After 1 month, so there is no relation. There is no that much relation which as earlier. So that is the case. There is no much correlation between the independent variables. I may clear these friends, Srikant, another Mansa and Srikant, Supriya, Sai Kumar, Sagiran.
Yes, sir.
Then as last day we discussed about what are the causes. Sometimes they will ask that, so what are the sources of multicollinearity, or what are the causes of multicollinearity, or sometimes they will ask what are the reasons for multicollinearity also. So generally as we discussed that the most of the economic variables move together in over a time, nothing but for a period of time. When you take some economic variables, generally if you take your income and your consumption, as your income increases, your consumption may also increases, right? In that case, you will get a multicollinearity problem. Okay, so sometimes if you take income, consumption, savings, investment, okay, so if you take this kind of variables, most of the economic variables they will move together in the long term. So that is the case, we will get a multicollinearity problem. And when you use the lagged values in your model also, you will get, for example, the present year consumption is depends on previous year consumption. See, if you take into account today consumption is depends on yesterday. For example, if you take your consumption today, for example, it is depends on the last day consumption, or this month consumption is depends on the last month consumption. But because if you have some habits to consume such kind of things, for example, if you take if you consume if you eat a chicken biryani in this month, you may eat the next month also, nothing but the next month expenditure is depends on the last month expenditure. So that is the case. We can get some multicollinearity problem when you are using the lagged value in the model. And statistical specification. For example, when you run the model, you should be clear that which model is appropriate and where we can use such kind of things. For example, if you take this is a thing, see, y is equal to beta 0, beta 1, x1, 2, and beta 2, x2, 3, beta 3, x3, t. So here I've used the squares, x2 squares and x3 squares. Okay. So for example, if you take in a consumption function, so the consumption function we cannot use the x squares. But whereas when you are applying models for the cost analysis or revenue analysis, we may need to use that squares. Okay. So for example, if you take here consumption, the consumption is depends on the income, right? Y is here C is for consumption, Y is called income, and CT minus one. This one consumption is depends on the previous year or previous day or previous month or previous week or previous quarter. So it depends on the your data, which data you have adopted. Okay. So I have considered as a year. You see, CT nothing but a present year consumption is depends on present year income, and present year consumption is depends on the previous year income. Sorry, previous consumption, right? So this is a term, as you know that. So should be clear that when you which model is appropriate for that your objectives. So that is the main thing we need to follow. So then, as you know that we discussed earlier also the data collection method and over determination model. What happens? So explanatory way. See, when you are taking into account the explanatory variables, then the number of observations. See, when you take into account, if you take more now independent variables rather than your number of observations. For example, if you have taken only 10 observations, if you take more than 10 independent variables, so you may get a multicollinearity problem. Nothing but when you are running a regression model, you should be clear that your observations are more than independent variables. For example, if you consider that one dependent variable, three independent variables. So you should be there, you should take more number of observations, nothing but you will take more number of data or number of years. So that should be, you should be clear that when you're taking into account. So then main topic, yeah, that is a consequence of multicollinearity. Earlier we discussed what are the causes. So what are the consequences? For example, if there is a multicollinearity problem existing in our model, what will happen? Right? So that is a consequence of multicollinearity. When there is a problem, what it could be, we can observe in the regression model. So that is a consequence of multicollinearity. So in cases of near multicollinearity, one is likely to encounter the following consequences. Okay, but when there is a high correlation between the independent variables, so how we can identify by looking at this model? The first one is that all the blue, that as you know that blue is the best linear unbiased estimator. So when you are estimating the values, so we need to follow certain assumptions also. As we discussed that in this model, there is a assumptions of classical linear regression model. There is a CLRM. So the OLS estimators have the large variance and covariance. For example, when you use the OLS method, so that have the large variance and covariance, making a precise estimate difficult. So here, see, when even if there is any multicollinearity problem in your model, if you estimate whatever you estimate the values, the estimation is difficult. Nothing but the results may give a wrong direction. Nothing but wrong interpretation also, and you get a large variance also. See, in the second one, because of consequences, there is a equation. The confidence intervals tend to be much wider. For example, if you take the confidence intervals, as we discussed in the how we can test the hypothesis, there's a confidence interval 90% or 95%. Okay, so the leading to acceptance of the zero null hypothesis, H0, nothing but H. There is a null hypothesis. We are going to acceptance because even there is a wrong thing also we need to accept. For example, when you are taking data, for example, or if I'm not wrong, see, in order to test your hypothesis, if you may conclude you have the hypothesis that is a there is no impact of income on consumption, for example. So generally, the income can impact on your consumption. That is the main thing. So when there is a multicollinear problem in your model, in that case, you may also accept it when you run when you are the H0, that is there is no relationship between the income and consumption. In that case, you need to accept your hypothesis. It means that, so you should be conclude that on the basis of your data, so there is no relationship between income and consumption. In that case, it means that when you are when the model, when particular model has been suffering from multicollinearity problem, so you need to accept your null hypothesis. So generally, as you know, that null hypothesis always we can frame and the negative way. Okay. So that is the thing, that the true population coefficient is zero more readily. So therefore, the case of multicollinearity, the sample data may compatible with a diverse set of hypotheses. Hence, the probability of acceptance of false hypothesis. See, so generally, I know that I had taught to you that in the second semester that there were about type 2 error, type 1 error. So here, when we are accepting a false statement, it means that, so probably accepting a false hypothesis. For example, somebody is wrong, somebody has done a wrong thing. If you accept, that is a, you are accepting a false statement, nothing but you are accepting a false statement. It means that your type error, that is called, the type error is a more dangerous. This is very important. See, when you are accepting a false statement or false hypothesis, that is called type error. This is a very important question which will come in the set net and other competitive exams. Please keep in mind that. Okay, when you are accepting a false statement or false hypothesis, that is called type 2 error. Type 2 error. What is type 1 error? So somebody has done good thing. If you are not accepting, if you reject, that is a type 1 error. Simple, I am going to say in Telugu, ఒక మంచి పని చేస్తే మీరు దాన్ని యాక్సెప్ట్ చేయకుండా నో ప్రాబ్లం. ఇఫ్ యూ రిజెక్ట్ ఇట్, దట్ ఇస్ ద టైప్ 1 ఎర్రర్. ఒకవేళ చెడు పని చేస్తే అది మంచి పని మీరు యాక్సెప్ట్ చేసారు అనుకోండి, దట్ ఈస్ కాల్డ్ టైప్ 2 ఎర్రర్. సో ఒకటే చెడు పని చేసిన వాళ్ళు మంచి పని అని మీరు యాక్సెప్ట్ చేస్తే అది టైప్ 2, విచ్ ఇస్ మోర్ డేంజరస్. Okay, so that is a type error. Please keep in mind, this is a very important question which will come for that net and set other computer exams also. Then third consequences, the also because of consequence of 1, so the t ratios of 1 or more coefficient tend to be statistically insignificant. So as we know, the t ratios, how we can identify the t values, that is the t statistic value. So I have explained in the second module, that is the t is equal to coefficient of beta by standard of beta. So that should be, we will get a statistic insignificant, nothing but we cannot get more than 2, or actually, so we cannot get more than 1.96. That is exactly, we can say at 5% level of significance. So sometimes when there is a multicollinear problem, we cannot get the particular independent variables which cannot significant. And although the t ratios of 1 or more coefficient is statistically insignificant, the R square and overall measure of goodness of it can be very high. See, sometimes when R square is also high, we need to check whether particular model is nothing but the percent of variation in dependent variable explained by independent variables particularly or not, nothing but we can check. We need to check that particular independent variables, all the variables can jointly influencing that dependent variable or not. So that is the case. We need to check the R square value also. When there's a multicollinear problem, we can get R square value is high. So for in example, in case of high collinearity, as estimated standard errors increases, the t value is decreases. Generally, the standard error value increases, the t value maybe decreases. So here, in that case, when the standard error is of standard of particular coefficient value is less, so we will get the particular variable is going to significant. Okay, that is the main thing we need to check. So how we can check the t value? See, the t is equal to estimated beta cap divided by standard of beta cap. Nothing but t is equal to the coefficient of beta divided by standard of beta cap or beta hat. So that we can calculate the t values. For example, if the t ratios is insignificant, the R square can be very high. Sometimes the particular independent variables are not influencing significantly, but R square can be high, more. So therefore, the contradictory conclusion in the presence of multicollinearity. So I may give the good example for you that in order to understand. See, the student cannot influence the teacher, okay, significantly, but the relation is nothing but the influencing capacity is high. See, that is the case, the R square. Okay, you may not influence me significantly, but you may changes in your nothing but the influencing is very high. Nothing but you may influence more me. So that is R square value. Nothing but the percent of variation on in me. So due to changes in your things. So that is the case. R square can be very high. So therefore, there is a contradictory conclusion. Nothing but you cannot influence me significantly, but the explanation power is very high. The explanatory power, nothing but the explanation power is very high. There is a model of goodness of it is very high. Okay, so that is the main thing. In Telugu, I can give that. మీరు నన్ను చాలా ఇన్ఫ్లుయెన్స్ చేయలేరు, బట్ ఇన్ఫ్లుయెన్స్ చేసే కెపాసిటీ ఎక్కువ చూపిస్తుంది. అక్కడ ఏంటంటే రిజల్ట్ ఒకటి ఉంది, చూపించేది ఒకటి ఉంది అనమాట. సో దట్ ఈస్ ద కేస్. దర్ ఇస్ కాంట్రడిక్టరీ conclusion we will get. So when there is a presence of multicollinearity, when there is a multicollinearity ఉన్నప్పుడు automatically this kind of situations we will get. Simple, in order to understand multicollinearity, so r square value ఎక్కువ ఉండి t value అనేది చాలా తక్కువ ఉంటే there is some multicollinearity problem. The fifth one, the wireless estimators and their standard errors can be sensitive to small changes in the data. So as you know that as per wireless order least square method estimators, their standard errors can be sensitive to small changes in the data. So as long as the multicollinearity is not perfect, estimation of regression coefficient is possible, but wireless estimates and the standard errors are very sensitive. So as we discussed that the wireless estimators and the standard errors are very sensitive to even slight changes in data. For example, if you change a slight changes in the data, for example, in order to if you convert the data into some different things, for example, if the data is not in the uniform, so you may get a multicollinear problem also. So if we change even only one observation, there is a drastic changes in the multicollinear values. For example, if you change a single value, so automatically there is a lot of changes in your coefficients values or t values and standard error values. So these are the consequences of multicollinearity. So dear student, have you understood what are the consequences of multicollinearity? Sai Kiran, Manasa, who is Redmi, Srikant, Supriya. Hello, Sai Kiran. సుప్రియ అర్థమైందా అర్థం కాలేదా?
అర్థమైంది సార్.
సాయి కిరణ్,
అర్థమైంది సార్.
మానస, శ్రీకాంత్. Okay, then we will come to know that how we can detect the multicollinearity. So here see there is a main topic, how we can detect the multicollinearity. How we can detect nothing but in the numerically how we can detect the multicollinearity. For example, when there is a causes unnai, when there is a consequences we have identified, then how do we check numerically? That is the main question which arises. For example, for graphical method we can see that, so there is a causes, there is some consequences we observe in the model, but how do we check whether the particular model is suffering from multicollinearity or not? The first one is the example the pairwise correlation. Nothing but we need to find out, we need to do the correlation matrix. Nothing but when there is a 3 independent variables, you need to run a correlation between x1 and x2 and x2 and x3 and x1 and x3. There is a pairwise one and one with another one, and you can use that F test to examine that giant significance of set of variables that are individually insignificant. So you can check the F test also. When you are under the multiple regression, you will get F test values, and more very important, that is a VIF value. VIF value, that is the VIF full form is variance inflation factor. Variance inflation factor, right? Yeah, variance inflation factor, variance inflation factor, which is very important. So sometimes they will ask the question, what are the tests of multicollinearities? VIF, F test, pairwise. Then fourth one, Ferrer-Glauber test. Ferrer-Glauber test. Then fifth one is a bunch analysis. So these are the tests we can use for the multicollinearity problem. So sometimes they will ask, what are the tests are multicollinearity? So you need to understand pairwise test, F test, VIF, Ferrer-Glauber test, and bunch test. So generally they will ask that match the followings also. Okay. So they one side they will give that multicollinearity, one side on the other side they will give the VIF and Glauber test also. So you need to match it. Okay. Yeah, we will discuss about pairwise and F test and VIF. See, one by one we will discuss. See, examine the pairwise correlation among the independent variables. How we can calculate that pairwise correlation? Simple, as I told you that there is a simple correlation matrix. Correlation matrix. If you can use by Excel also, you will get it correlation matrix. So simple, I have done. See that pairwise x1 and x2, x1 and x2 variable. See, there is a relationship between x1 and x2 is how much? 0.9958. This is the first one. Okay. So I have done the another one, x1 and x3. x1 and x3. What is the relation between 0.99588? Okay. So when there is a relation between x2 and x3, 0.995882. Okay. So this is fine. See, when you observe this value, there is called R value. There is a correlation value 0.099, which means that which are equal to 1. 99.95. Sorry, 0.9958 means that 99%. Okay. So there is some perfect correlation between x1 and x2 also. Here, if you observe that x1 and x3, there is a perfect collinearity here. x2 and x3 variable, you can like you need to check like this: x2 and x3. So this is R value 0.958. So here also there is a perfect multicollinearity problem existing in the model. So in that case, we can clearly observe that the model has been suffering from multicollinearity problem. This is a pairwise correlation, right? Then F test. So when you are running a model, multiple regression, you will get F test values. So insignificant regression coefficients for that affected variables in a multiple regression, but a rejection of giant hypothesis that those coefficients are all zero using F statistics. So as I discussed that, see, when we are running a regression model, so in that case, as I told you that rejection of the giant hypothesis, that those effect coefficients are all zero. For example, when you are rejecting the hypothesis, when coefficient is equal to zero, what it means that your coefficient value is zero, beta 0 is equal to 0, so beta 1 is equal to 0. It means that the independent variables is not affecting on the dependent variable. Okay. So here, when you are accepting giant hypothesis that the coefficients are all zero using F testing, you can know that the particular model has been suffering from multicollinearity. Then this is a very important. Clean observe that VIF, which is very important. VIF, as I told you, that variance inflation factor. Variance inflation factor. So here, some of the authors suggested the formula detection tolerance or variance inflation factor for the multicollinearity. How we can find out the multicollinearity problem? So by using VIF values only, the softwares will give the VIF value, but we need to understand how we can calculate the VIF also. I will show you. So as we know that VIF is a measure of effect of multicollinearity on variance parameter estimate. See, so why we can estimate the VIF values? So here we need to know that how much the effect of multicollinearity on variance parameter estimate. I think that when you are estimating the parameters, that is the coefficient values, how much the effect of multicollinearity on estimated coefficient values. Then if you find out high VAF suggests the presence of multicollinearity. When you get VAF values are high, so you may conclude that there is a high multicollinearity problem. When VAF value is more, okay, there is a multicollinearity problem. So generally, if VAF value is more than 2, usually indicate multicollinearity problem. Okay, if you get more than 5 or more than 10, so which has a serious multicollinearity problem. So VAF shows that how the variance of the estimator is inflated by the presence of multicollinearity. Nothing but when your VAF value, what it shows that the variance of the estimator, nothing but how much the variation of the an estimator is inflated by the presence of multicollinearity. Presence of multicollinearity. Then I will show you that how we can calculate the VAF. So simple, you can write the formula. VAF is equal to 1 divided by 1 minus r square. 1 divided by 1 divided by 1 minus r square. 1 minus r square. See here, when you run the multiple regression, simple you will get r square value. Okay. Then on the base of r square value, you will find out the VAF values. Okay. So VAF value we will get in EV software. But if you run in simple other models also, other for example, if you run Excel file, so you may not get VAF values, but when you run a Excel software, you may get r square value. You will get r square value. On the base of r square value, you will find out how much the variance factor is there. Variance influence factor is there. Value, how much VAF value is there. Or else you will get another formula. VAF is equal to 1 by tolerance. 1 by tolerance. So tolerance is another value. So we will find out how the tolerance value is there. Okay, so simple, you can remember these two are very important, VAF and tolerance. So here, as I'm showing that if there is no multicollinearity between x2 and x3, VAF will be 1. For example, see, when there is no relationship between the independent variables, the VAF equal to 1. VAF value equal to 1. So if there is no multicollinearity between x2 and x3, the VAF will be 1. A tolerance of less than 0.20 or 0.10. For example, if you get a tolerance value 0.20, 0.10, the VAF value 5 or 10, the above indicates the multicollinearity problem. For example, if you get VAF value is more than 5 and 10. For example, if you take both values, it's considerable. If you get VAF value is more than 5 or 10. So that indicates that your model has been suffering from multicollinearity problem. Your model has been suffering from multicollinearity problem. So I'm going to show that what is the tolerance value. As you know that the tolerance is equal to 1 by VAF, 1 by VAF, or 1 by 1 minus r square, 1 minus r square. Tolerance is equal to 1 minus r square or 1 by VAF. VAF is equal to 1 minus 1 by r square also you can get it. Okay. As I told you earlier. So we need to check, for example, so you can find out, you can note down that is the inverse of VAF is called tolerance. Inverse of VAF is called tolerance. This is a very important topic. Thing that inverse of VAF is called tolerance. There is a in mathematics in presentation in the publication of articles or other things, they will publish only TOL. There is a tolerance value. Okay. So if r square is 0.8, the VAF would be, for example, sometimes they will ask the questions. If r square value is 0.8, r square, maybe sometimes they will put 2 here, r square is 0.8, the VAF would be. Can anybody can say that? Hello? Saikiran, Jaipal, Manasa, Srikant, Supriya. Can anybody can say that? If r square is 0.8, the VAF would be. You can apply this formula. See, VAF is equal 1 by 1 minus r square. What will happen? Simple, VAF is equal to 1 by 1 minus r square is equal to how much? 0.8. 0.8. So then see is equal 1 minus 1 by sorry 1 is equal to 1 divided by 1 minus r square is equal to how much? 0.8. So as it is as it is 1 divided by so 1 minus 0.8 0.2. Then 1 by 0.2 how much? 5. So when VF value is 5, what you can suggest? So the particular model has been suffering from multicollinearity problem, right? When VF value is 5 or more than 5, indicate that the particular model has been suffering from multicollinearity. Simple, if R square is 0.8, the particular model would be suffering from multicollinearity problem because the VF value shows 5. Okay. So sometimes we will consider less than 5 also. There is no multicollinearity problem much. Then another example I am going to show that, see, if VA value is 5, what is the tolerance would be? Sometimes they will ask such kind of question. If VA value is 5, the tolerance would be, how, what is the tolerance value here? Seeing tolerance is equal 1 by VAF. Tolerance is equal to 1 by VAF. 1 by 5, how much? 0.2. So here 1 by 5 is equal to how much? 0.2. Another example I am going to see tolerance. So another formula like this, 1 minus R square. See, same thing. So here the tolerance is equal to 1 minus R square as I told tolerance value. So sometimes they will give the VA value, sometimes they will give the R square value. If R square value is 0.8, the tolerance would be అడగవచ్చు. So you need to substitute this one 1 minus R square value. So see. So same thing we have taken, only R square is 0.8 and VF is 5. You can find out the tolerance is 0.2. Here 0.2. So ఏ వాల్యూ ఇచ్చినా మనం కనుక్కునేటట్టు ఉండాలి. So simple you can remember this thing which is very important for you. So here if the value of the tolerance is less than 0.2 and 0.1, see here this one tolerance value. Simultaneously the variance, the value of AF 5 or 10 and above, then the multicollinearity is existing. Okay. So generally if your tolerance value is 0.2 or 0.1, the particular model has been suffering from multicollinearity problem. The another test, that is the Farrer-Glaber test. So here it is a combination of 3 tests. It is a combination of 3 tests. There is a chi-square test, F test, and T test. Please remember that it is really to a set of 3 tests. Farrer-Glaber test, it will be concluded on the basis of chi-square test, F test, and T test. So that the author is used 3 statistics for testing the multicollinearity. So the Farrer-Glaber, the people, those who had introduced this test is based on the 3 tests: chi-square test, F test, and T test. Please remember. So why they can use the chi-square? So in order to identify that the chi-square test for the detection of existing and severity of multicollinearity, severity. It means that how we can detect the multicollinearity. First, that's why they can use chi-square. Why they have used the F test? F test is locating the which variable or multicollinear. I think, but when they are using the multiple regression, so when you're using the Farrer-Glaber test, which variable is having more multicollinearity problem? Nothing but which variables are more collinear. Nothing but which variables are more correlated each other. That's why they will use F test. Then why they can use that T test? So here T test is for finding the out pattern of multicollinearity. What is the pattern of multicollinearity is there in our model? So that's why they will use the 3 tests. Sometimes they will ask that why they can use the chi-square test for the Farrer-Glaber test. So in order to existing and severity of the multicollinearity, why they can use the F test for in the Farrer-Glaber test for locating which variables are multicollinear. Okay, so please keep in mind this is very important. So generally, as I conclude that if the variables are found to be orthogonal uncorrelated, for example, if the variables are not correlated, there is no multicollinearity. Okay. If the variables are not orthogonal, it means that when the variables are not correlated, so then the list of some degree of multicollinearity is presented. So as per C. Robert Richards,